Yes, good afternoon. Am I audible?
Yes, sir.
Yeah, and my screen is also visible, right?
Yes, sir.
Okay. So this is assignment 6. We'll discuss assignment 6 problems now today.
Yes, sir.
So we'll start with question number 1. Which of the following statements are true? Okay. V be an infinite dimensional space. Just a minute. Yeah. V be an infinite dimensional space, and if n is any positive integer, then you collect some finitely many points, and there exists a non-zero functional f naught such that f naught at xi is 0 for every I going from 1 to n. So this is an application of Hahn-Banach separation theorem. What we do is we'll create W to be span of those xi's. And W is a finite dimensional subspace. Okay. And now if you take any x naught belongs to whole space V minus W, because V is infinite dimensional, hence W has to be a proper subspace. So there exists some x naught belongs to V minus W. And by an application, or what do you say, corollary of Hahn-Banach separation theorem, there exists f naught belongs to V star such that f naught restricted to W is identically 0, but f naught is non-zero. Okay, so this is what we wanted, right? Because if f naught restricted to whole W is 0, f naught will be 0 at every point xi, because W is basically generated by those xi's. This is true. Second, every weak star open neighborhood of the origin in V star is unbounded. Okay, so second. Okay, first, how, I mean, see, the basic thing is, if suppose the claim is, if we prove the statement for basic open sets, then we are done. Why? Because every open neighborhood contains a basic open set, and if a basic open set is unbounded, then the whole set is also, then the open set will also be unbounded. Okay, so we'll just consider any basic open set. Let U be a basic weak star open set containing 0, 0 of V star. Okay, that means U is equals to what? It will be some xi hat inverse of some open set, open neighborhood of R containing 0, 0, right? But I mean, I can, without loss, I can take this as minus epsilon epsilon section I going from 1 to n. Okay, where xi hat are a functionals. Okay, xi hat are defined from basically x hat, if I say x hat are from V star to R or C, whatever, such that x hat at f is equals to fx. These are the functionals by which we form the weak star topology. These are the generators of weak star topology. So any basic open set is just intersection of finitely many inverse images of minus epsilon to epsilon. Okay. I can think of it like that without loss of generality. Even if I prove for this kind of open sets, I'm done. Okay. So what again if I write U in some different way? So U is here subset of V star. So U is set of all F belongs to V star such that modulus of F at Xi is strictly less than epsilon for all I going from 1 to n. Okay. So suppose these are the finitely many points, right, from 1 to n, Xi. Suppose I can find a functional f naught belongs to V star such that f at Xi is 0 for I less equal 1 to n. Okay, then what I can say, and suppose f naught is also non-zero, then for any alpha belongs to R, alpha f naught is also non-zero. I mean this. And what is the norm of alpha f naught? Is mod alpha norm f naught, which will goes to infinity as alpha goes to infinity, right? So if I get such an f naught, then I can say that U is unbounded, right? Because then this alpha f naught will also belongs to U, okay, for all alpha belongs to R, since it's zero only. Okay, but guaranteeing like the guarantee of existence of such an f naught is from the first option, right? This one. Okay. If you collect some finitely many xi, then there exists an f naught such that f naught at xi is zero for every I going from 1 to n, and like separation theorem. So there exists an f naught such that this happens. Now you multiply that f what do you say f naught by any alpha. Alpha f naught again will be in the U, and alpha f naught is unbounded. Like alpha goes to infinity, norm goes to infinity. So second statement is true. Every weak star open neighborhood of origin is weak star is unbounded. Now we have to check about weakly open neighborhood. Similarly, like of V star, for weak open also, we'll just check for basic open sets. If the statement follows for basic open sets, we are done. Okay. So basic open set here will be what? Intersection of Fi inverse of minus epsilon to epsilon, suppose. I going from 1 to n. Okay. Also can be written as set of all x belongs to V such that Fi at x modulus is strictly less than epsilon for all I going from 1 to n. Okay. So this is a basic open set. I mean, kind of. Now, I want to show that U is unbounded. Okay. I mean, so now I'll take W to be set of all x belongs to V such that Fi of x is equals to 0 for all 1 less equal I less equal n. So this W is contained in U. Okay, this is a U. Is it non-empty? Because see, Fi at 0 is 0, right? For all I. Like for every linear function, in fact, 0 goes to 0. So singleton 0 will always be contained in W. My claim is this W cannot be just singleton 0, it's more than that. Okay, it's a proper non-trivial subspace of V. Okay, so if I prove if you prove that W is non-trivial, then since it is a subspace, it is unbounded. So you have a subset of U which is unbounded, hence U will be itself unbounded. Okay. So for proving W as non-trivial, we'll consider mapping phi from V to Rn given by phi at x equals to f1 of x comma f2 of x like this fn of x. Okay, so now this mapping cannot be 1 1. Okay, since range of phi is finite and V is infinite dimensional. Now, but what is kernel phi? Kernel phi is our space W. Therefore, X for which component wise each and every component 0, which implies this. This is the kernel. So kernel is not singleton 0, which implies we are done. U is unbounded because U contains W, which is unbounded. Okay, this is clear. Question number 1, 1, 2, 3, all are correct. Okay, any doubt in this?
No, sir.
Okay. Okay, so question number 2, where B naught be the closed unit ball in C naught. Okay, so here C naught is space of all sequences which converges to 0. Okay, and B naught, if you consider B naught is closed unit ball, right? So like Xn belongs to C naught such that modulus of Xn is less equal 1 for all n. So we have to prove that B naught is closed in L infinity. Okay. So first what we know is B naught is given as closed in C naught, right? Because we are taking it as a closed unit ball of C naught. Okay, but the closed unit ball of L infinity, say B naught tilde. Okay, then what is this B naught? B naught is just B naught tilde intersection with C naught. Okay, and what do we know about C naught? C naught is closed. We have seen it in some session before, maybe fourth or third assignment, I guess. So C naught is closed, which implies B naught being intersection of two closed sets, it is also closed. Okay. Second thing is B naught is weakly closed in L infinity. Okay. Actually, last time also, I think we have seen this theorem. Like any let C be convex subset of X. X is a nonlinear space. Then X is weakly closed if and only if X is non-closed. This is a straightaway application of Hahn-Banach separation theorem. You can try it. Also, I think I have explained it in last session, this the proof of this theorem. Okay. So here it is straight away clear that this B naught is convex and B naught is given as B naught is convex, and from first option it is closed. Hence it will imply that B naught is weakly closed. Okay. So now we have to check whether B naught is weak star closed. Okay. So when you consider a weak star topology on something, that space has to be considered as a dual space of some pre-dual space. Okay. So when I say weak star topology L infinity, I'm thinking of L infinity as L1 dual. Okay, you can also say C naught dual, maybe that's fine. Okay. And B naught, when I say here, this B naught is not just a closed unit ball in C naught. Okay, this B naught in when considered as a weak star set in L infinity, this is set of all functionals from L1 to R such that like f at every element x is given by summation xj yj j going from j equals to 1 to infinity, where yj is from the before set B naught, that is yj goes to 0 and j going to infinity, and modulus of yj is this equal 1 for all j belongs to natural number. Okay, like kind of when we say a dual of L1, we identify every linear functional with an element in L infinity, right? This identification is this y. Like for every f, there exists this y that is identified as an element of L infinity. So when we say B naught straight away as a subset of L infinity in the way that L infinity is a dual of L1, we kind of relate this B naught with a subset of direct L infinity. Okay, but this is the set of functionals, not just set of sequences. Okay, that's the conceptual difference you have to think of. Okay, so now the claim is that this B naught is not weak star closed. Okay, first of all, weak star closed means what? If you take any sequence, first of all, suppose Fn belongs to any vector space X star, then Fn converges to F weak star. Okay. Like in weak star topology, Fn converges to F if and only if Fn at X goes to Fx for all X belongs to space X. This is the definition of weak star convergence. Yeah. Okay. So my claim is this is not like B naught is not weak star closed. So I'll give a sequence of functionals which converges to some function f, but that f is not in B naught. So if define a Fn as like kind of Fn corresponds with okay, we'll try with this 1 1 1 up to n times then 0. What that means, Fn is defined as Fn at x equals to summation xj, j going from 1 to n. Okay, like I mean this yj is replaced by 1 here from 1 to n, otherwise 0. Okay, these are the linear functionals Fn, and you can see these Fn's belongs to B naught. The question is, where does it converge? Or even if it converges somewhere. So see, you can, from here it's straight away clear that Fn at x converges to being sequence of partial sum of this series summation xj, going from 1 to infinity. This converges to j going from 1 to infinity xj. Okay, but f defined as fx equals to summation yeah, okay. And this belongs to L1 dash actually now. The problem is, okay, we'll change something. We'll define Fn like this: 1 by 2 till 1 by n. Yeah, yeah. This should converge to here. Yeah, yeah. But this f is identified with the element 1 by 2. This sequence, 1 by n sequence. Okay, but this sequence doesn't belongs to L infinity, right? Hence, f cannot belongs to L1 dash. Oh, sorry, sorry. Okay, we want L infinity to be L1 dual. Just a minute. Hmm. Okay, this is not example, counter example. Okay, think of some else other counter example. Okay, this doesn't work. What I'll now think is, suppose Fn is defined like this: Fn at x equals to xn. Let's see if this works. Okay, so now since x belongs to L1, Fn at x converges to 0, right? As n going to infinity. Okay, that means hmm, okay, this also can be thought of C naught dual. I want to give a sequence Fn which converges to F in star. This also doesn't work. The aim is to find Fn to C naught dual. There is something problem in this. Question number third. Okay, I'll get back on this later. Go to question number third. Part two, third. I'm not remembering what was the counterexample. Just a minute. Okay, there is no counterexample given. Okay, I'll provide the counterexample in the notes later on when I upload these notes. Okay. So just for as an answer, that space that V naught is not weak star closed. Okay. There's a big theory involved there, but I'll give a simple counterexample in the notes. Okay. So question number three. Which of the following statements are true? One, the space C naught is reflexive. Okay. So is it so? So what is C naught dual? It's L1. Oh, sorry. Yeah. Oh, if by mistake, oh, okay, I said here C naught dual is L infinity. Actually, it's not. C naught dual is L1. Okay. C naught dual is L1, and what is L1 dual? It is L infinity. But see, space being reflexive means what? C naught and L infinity must be kind of isomorphic, right? But L infinity is non-separable.
Reflexive also, sir.
Yeah,
L
yeah,
infinity is not. L
yeah.
infinity is not reflexive, sir.
Correct, correct. L infinity not reflexive also. Hence, C naught not also cannot be this thing reflexive. Okay, this is wrong. Third part B is the space C is reflexive, but by the same logic, we can say C is non-reflexive. Then the third is the space CC over R is not reflexive. Yeah, this is correct because space CC over R is not Banach space, right? We know it's we have seen in the first or second video that space CC over R's closure is C naught over R, right? So because if CC over R is reflexive, then CC over R is isomorphic with its double dual. But double dual being set of a linear functions from a vector space to a Banach space R, it will be Banach space, but this is not. In space CC over R is not reflexive is correct option. Yeah. Which of the following statements are true?
Sir, how the space is not reflexive, sir?
Excuse me. Okay, space C you're asking, huh?
Yes, sir. Second option.
Yeah, because it has C naught, right? C naught is a closed subspace of C. So if a space
Yes.
is reflexive, then its closed subspace will also be reflexive. Okay.
Okay, sir.
So the theorem here you can check is closed subspace of reflexive space is reflexive. Okay. Hence C naught is a closed subspace of C, which implies C is non-reflexive. Now question number 4. Which of the following statements are true? The space C01 is separable. Yeah, this is just Bolzano Weierstrass theorem.
Sir, screen is not visible, sir.
Screen is not visible
Screen is not visible, sir.
now.
No, sir.
Y is equal to maybe some internet problem with your side, because for me it's visible on my PC. Try to rejoin again.
Okay, sir. I will check, sir.
Yeah, try.
Okay, sir.
Yeah. So the space C01 is separable because you have a countable dense subset here, which is set of all polynomials with rational entries. Okay. Then the space C0 is separable. Yeah, this is also true. Okay, I'll just prove this one maybe. All other proofs will be on the same line of this one. Space C0 is separable. So the claim is to take set of all sequences xn such that xn is equals to 0 for all n greater or equal to some capital N. Okay. Like after some time it vanishes. This n depends individually for each x, and xn belongs to rational number. A kind of C0 not space with rational entries. Okay. Yeah. So the C0 not space with rational entries. This set is simply C0 not. So how is the claim is this set is dense. Set is dense in C0. This is countable, that's for sure, because I'm just taking uh, entries from rationals, and finitely many terms are non-zero, other every term is zero. So and then taking the union. Okay. So it's just q cross q for some n, and then union of this over n belongs to natural number. So countable. Okay, so this set is countable, and my claim is that this set will be dense in C0. Okay, so let any x belongs to C0, the and for any epsilon positive, there exists some capital N, so that modulus of xn will be strictly less than epsilon by 2 for all n greater or equal capital N. Okay, or I'll just take epsilon. No need of epsilon by 2. Yeah. Now what I'll define is, let y defined like y. Okay, before that, now after n, all x mod xn's are less than 0. Okay, we want to find a y with rational entries in C0 such that norm of x minus y we want less than epsilon, right? Okay, if I do that, then I'm done. Okay, so see, if I put like just I'm creating y step by step. If you think, if I put if y at I, if I put 0 for all I greater or equal capital N, then what I'll get? Then modulus of xi minus yi will be modulus of xi, which is strictly less than epsilon for all I greater or equal capital N from this. Hence, after capital N, I'm done, right? Only from 1 to n, I have to think how to create y, right? So basically, because there are just finitely many entries, so and xi is itself is a real number, so there exists yi, like I choose rationals because rationals are dense in reals. Y belongs to Q such that modulus of xi minus yi is strictly less than epsilon for all 1 less equal I less equal capital N. Right? For first n terms, I practically choose a rational points yi and then create this y. Right? So now this y belongs to C naught naught with rational entries. And norm of x minus y is strictly less than epsilon. So I'm done for any epsilon ball containing A, there exists a point y from this set which is countable. And hence it will be a dense. So C naught is separable. So exact same lines will go for LP, but from P1 to strictly less than infinity. Okay, L infinity is there, hence this is not separable. Okay, okay, I will give a quick proof of why L infinity is not separable. So L infinity is not separable. So it's not separable means there cannot exist a countable dense subset of L infinity. Okay, how I will do it is you just take any real number. Suppose R belongs to open 0, 1. Okay, and you write a binary representation of this R will be like some zeros and one, right? Some zeros and ones, like this. So for every such R, you can define a sequence, right? Xn, like yeah, if this is one, at first position you have one, then one. At second position you have zero, then zero. Simply this one, zero, one, one, like this. Like same this binary representation, you put it in here. So this is a sequence. So for every real number in 0 to 1, you can define this uncountably many, sorry, not just sequence, this X element, actually, element of L infinity, because the supremum is 1, right? It's just 1 or 0. So for every real number in open 0, 1, you can define an element in L infinity, right? So there are uncountable many elements here, and difference between any two elements there is 1, correct? Because for two distinct real numbers, there is at least one entry for which there is no I mean there exists at least one entry which differs in the value of 1 or 0. Okay, that means difference of any of these two kind of points is 1. So if you take a ball centered at any point with radius okay, not like that. So let D be dense in L infinity. Okay, then for any element y belongs to D, ball centered at y with radius half contains at most one element of this type, right? That means we have uncountably many such elements. So to cover all such elements, you need uncountably many elements in here in D. So every dense subset of L infinity is uncountable, hence it cannot be separable. Okay, so this is the overview idea. You try to fill in the gaps. Is it clear? Any doubt in that? Hello?
Yes, sir.
Yeah, any doubt in that previous one?
Sir, second one, sir, second option, sir.
Second option, why C naught is separable?
Yes, sir.
So what is the doubt in that?
Sir, I can't understand, sir. I am rejoined, sir, so I can't understand that one, sir.
Okay, okay, okay. I'll just explain once again.
Okay,
So
sir.
you take C naught as a separable. We want to prove that C naught is separable. Okay. So I am practically creating a countable dense subset here. Okay. So C naught naught is just a set of all sequences such that only finitely many terms are non-zero. Other than that, every term is zero. Right? But in that also, I'm taking such sequences with rational entries only. Okay. So that set will be countable. Okay, by this logic. Now my claim is that the set is dense also in C naught. Okay. So how I will prove that the set is dense? If I take any point of C naught and take any epsilon neighborhood around that point, I should get an element from the set in that neighborhood, right? So I took a point x belongs to C naught. Now for any epsilon positive, because x is in C naught, it goes to 0 as in goes to infinity. Hence there exists a capital N such that modulus of xn is less than epsilon, right? So now I want to find a y, right? Belongs to C naught naught. So yeah. So I'm looking practically to find so how to define that y, right? So in a case, if I define yi as 0 for all I greater equal capital N, then what will be modulus of xi minus yi, which is just modulus of xi, and from here it is less than epsilon for all I greater equal capital N. So after capital N, y's are all 0. That's fine to define. So before capital N, you have only finitely many points from 1 to capital N. And since rational number set is complete in reals, so I can get such yi's for this xi such that modulus of xi minus yi is less than epsilon for all I 1 to n, right? So like just finitely many points are there. I'll just for each point xi I'll find the closest rational number yi. Okay, and then I'll define the whole y. That y is now dense. Sorry, that y is in the epsilon neighborhood of x. Okay, because for each I mod xi minus y is less than epsilon. So I'm done. Okay. The set we defined is countable as well as dense in C naught. Hence, C naught is separable. Okay. I hope you understand this. If not, you can watch. Just watch again.
Yes, sir. Yes, sir. Thank you,
Yeah.
sir.
Okay. Okay. So question number fifth. Yeah, just a minute. So question number fifth says, which of the following statements are true? Okay. So first option is if a Banach space V is separable and if V star is not separable, then V is not reflexive. Okay. You should know a theorem here ki if x Banach, not if, then x star, yeah, because if V is reflexive, yeah, yeah. So x star separable implies x separable. Okay. So now consider in this part one, if suppose here we consider that V is reflexive, huh? So V reflexive and we know that V is separable. What does it mean? That means V star star is separable because they are just isomorphic. But V star star is what? You can think of it as V star ka star, right? And from this lemma, then this follows that V star is separable. But they have given that V star is not separable. That means this cannot happen. Oh, sorry. That means this is true. That if V is separable and if V star is not separable, then V is not reflexive. We had started with V being separate, reflexive. Okay. Second one.
Sir, the space L1 is separable, but L1 star, L infinity is not separable.
Yeah, yeah. The theorem I said here is in converse part. Like if dual is separable, then the space is separable. What example you gave is x separable. X separable doesn't imply x star separable. the reverse thing. X star separable implies X separable. Like if L infinity was separable, then we could have said that okay, L1 is separable. But L infinity is not separable. Okay?
Okay, sir.
Yeah, yeah. So option B now, which says let V be Banach space. If there exists an uncountable set S, subset of V such that norm x minus y is 2 for all x comma y, then V is not separable. Yeah, this is just same as we have done for to showing L infinity is not separable. Like you have a countable subset such that any 2 points are of distance 2. So any dense set must contain uncountably many elements to cover all such points, all of S. So it cannot be separable. Okay. This is clear, right? Second option. Hello?
Yes, sir.
Yeah, second option is clear, right?
Yes, sir.
Okay. So, third one. If V and W are Banach spaces which are separable, then L over VW is separable. Oh, this is wrong. For counter example, we can take V to be L1 and W to be R, just R. So L of VW will be just dual of L1, which is L infinity. So not separable. Okay. This is question number 5th. We'll go to question number 6. V equals to C01 for x belongs to 0, 1, define. Okay, these are functions in V star. I have to prove that distance is 2. Okay. So what is norm delta x minus delta y? It is supremum of all delta x minus delta y at f. Right? Delta x is a function of V to R, where f belongs to C01. Norm f infinity is less equal 1. Okay. But what is this? Delta x minus delta y at f is just fx minus fy, which is less equal modulus of fx by triangle inequality, modulus of fy, which is less equal. This is norm f infinity plus norm f infinity, which is 2. So like this is for sure that supremum is less equal to. I want to show it's equal to 2. So I need a function f which is okay. So if suppose if we find f belongs to C01 such that norm f infinity is 1 and f at x is 1 and f at x is minus 1. Sorry, f at y is minus 1. Then what I get? Modulus of delta x minus delta y at this f will be equals to is equals to 1 minus minus 1 plus 1, which is 2. Okay, then I'm done. So how I'll find this f is, so yeah. So for any x and y, suppose x is here and y is here. So how I'll define this function is from Yeah. So from 0 to x it is 1. And from x to y you take linearly -1, and then from here it's -1. Yeah. So this is this f belongs to C01, right? And norm of f infinity is 1, and I'm done. F at x is 1, f at y is -1. Right? This I can define for any x and y, right? There is no condition on x and y. That means this norm is 1, this norm is 2. Okay. Now option B. If V is as above, then V star is not separable. Yeah. We just, if you collect set of all these kind of functions S, then S is uncountable, S is uncountable, and distance between any 2 points is 2, which means by previous option, some question number 5th, I guess. Yeah, see. Question number 5th. By 5th part B, V star cannot be separable. Because if you have an uncountable subset which are equidistant, like for any 2 points in that set is of distance 2, so there cannot be a countable dense subset to that space. Okay. So I hope this is clear. And the next option, okay, so this is correct. If V is as above, then Vista is not separable. Okay. The next question is the space C01 reflexive? Okay. Oh no, same logic. See, uh, if C01 is reflexive, then we know that C01 is separable also. That means C01 double dual is also separable. And from the previous lemma which I have seen, C01 star का star separable implies C01 star is separable. But right now we have seen that C01 star is not separable because this is an uncountable set in C01 star which is at equidistance from each other. Okay, so C01 cannot be separable. This is contradiction. C01 cannot be reflexive. Okay, so any doubt in this one? Okay. Question number 7. So let Xn be a bounded sequence in L1. That means it is kind of sequence of sequences. Okay. Because L1 itself is a collection of all sequences. Now if Xn converges to X weakly, then for every positive integer, Xnj goes to Xj. Okay. So what they are saying is simply Xn is a sequence. Okay. So like X at 1 is this sequence, X11, x2 2, sorry, x2 1, like this, x and 1 going on, then x2 is this. This is how we have the sequence xn. Okay. So what they're saying is if xn converges to x pointwise, then this pointwise sequence also converges. This. Okay, for each j, if you fix x n j, say this is x11, x12, x1n, so should converge to x1. This x2n converge to x2. Like this should happen. So this is what the statement means. Okay. So this is first of all what we know is xn converges to x weakly. Like I mean like in weak topology. Okay. Yeah. So in weak topology, xn converges to x. That's what we know. That means f of xn converges to fx for all f belongs to this is L1, right? Yeah, L1 star, right? Weak convergence. Because of weak convergence. Now, if I define fn, suppose, or yeah, I'll call it xj, fj, sorry. Fj I'll define from L1 to R as fj of any sequence x is equals to xj. Like jth component of that sequence x. Okay. So this fj is linear, continuous. So it's in fj belongs to L1 star. Okay. And what is fj of xn? Oh, sorry. Yeah. Fj of xn will be xjn. This should converge to fj of x, which is xj. Yeah, so that's clear. Xjn, xnj goes to xj. This is happening for all j belongs to natural number. Okay, that means the first option is true. Just the definition of weak topology I have used. Okay, because in weak topology, every continuous linear functional is weakly continuous. That's all. The second one is let xn be a bounded sequence in L1 if for every positive integer j. Now, if the converse part is happening, suppose that the component-wise sequence xnj is converging to xj, then is it true that xn converges to x? Okay. Weakly. So this is not true. Example is, okay, let's see if this works. Xn is simply en sequence. Oh, no, no. Yeah, en sequence, like defined as uh, like nth position 1, not like this. Okay, like what will be E1? 1 0 0. So here what you can see is for each component x and j is converging to 0, right? So we can think of that this ENs should converge to 0 functional, right? But let's see if that goes. Yeah. Okay. So if I define function f from L1 to R as f of x equals to let's say summation xj. Yeah, this is in L1 star. Uh, but f of En is what 1 for all n belongs to natural number, so converges to 1. But what is f at 0? 0 sequence it is 0, right? So f at En does not converges to f at 0, right? So it disproves the second option. Okay, xnj converges to x at j, but xn doesn't converges to x weakly. Okay, now third one. Third one, they're asking hmm, that xn is weak star convergent in L1. Okay, so when you talk about weak star topology on a vector space, you can think of that topology as a dual of some other topology, right? Because weak star topology you give on a dual of a vector space, right? So when I say L1, I'm describing it as a dual of C naught. Okay. So now the meaning of this xn also changes somehow. Okay. So this xn is sequence 1 1 by n. No, just this. So this xn belongs to L1 for all n belongs to natural number because they're just finitely many non-zero terms and fine. But when you think L1 as C naught dual, how do you identify? C naught dual is simply set of all functionals from C naught to R, correct? But yeah, but you know C naught dual is L1. That means for every f belongs to C naught dash, there exists some y belongs to L1 such that f of x equals to summation xj yj, right? J going from 1 to infinity. So kind of every linear functional is associated with this y, right? So when I say now this xn as a subset of L1, which is like C naught dash, that means this xn is the functional, can be related with this functional fn given by fn at x equals to summation xj upon j going from 1 to n, right? So this is the sequence. If you uh, put that sequence here, what do you get? This thing. Okay. Yeah. So now you have the sequence in C naught dual, right? So Fn is you have in C naught dash, and you have to check whether this Fn converges, I mean weak star. Okay, but see, in weak star converges, you have a result that the sequence Fn converges to F in star if and only if Fn of x goes to Fx for all, and like for all x belongs to space, where here it is C naught. See, but what intuitionally you can think Fn of x is summation xj by j going from 1 to infinity. Like kind of where this should go, this should go to summation, like here it was n, xj by j, right? J going from 1 to infinity, right? But this need not belongs to dash. Why? Because if it belongs, then from the identification we have, here we get the sequence as 1, 1 by 2, 1 by 3, so on. Same. This doesn't belongs to L1, right? That means this Fn does not converge. Okay. So kind of intuitive, you have to think about it. Also, I can give some other argument here. Uh, yeah, see, in other argument, if you want to see the same example, same thing. So I want to show that this Fn cannot converge, cannot weak star converge in C naught dash. So suppose, on contrary, suppose this Fn converges to F star. This implies Fn at x converges to Fx for all x belongs to C naught, right? Now I'll define, uh, yeah, okay. So and what is the property of f? Modulus of fx should be less equal norm f into norm x, right? We should have if f belongs to C naught dash, right? So define new element x, suppose uh, as, okay, I call this element as xm, suppose as xm I is 1, 1 less equal I less equal m, and then 0. Okay, so what is fn at m? So what is fn at xm, which is summation I going from 1 to m 1 by j, right? Whenever n is greater or equal m, yeah, yes. So this xm is fixed. This is a constant now. Hence, that means what? Fn converge to f. That means modulus of fx, right? Not this, just modulus of xm is less equal norm f, because norm xm is 1 for every m. This should happen for all m belongs to natural number, right? But this xm in particular, as m goes to infinity, it's unbounded, right? Because the series 1 by n is unbounded, right? So this is a contradiction, because you are getting that the series 1 by j is bounded from here. Okay, this is just another argument to show that space the sequence Fn is not weak star conversion. Okay, so is it clear? Okay, let's go ahead. Question number 8. Which of the following statements are true? Let V be a Banach space. If Fn is weak star convergent in V star, then the sequence is bounded. Just a minute. Yeah, okay. Yeah, so what we have is V Banach space. Fn is weak star convergent. Okay, that means Fn converges to F, suppose star. So we have seen just now that Fn converges to F in weak star topology means Fn at X converges to Fx for all X belongs to V, right? That means this family is pointwise bounded. V is Banach, hence by a uniform boundedness principle, this Fn is bounded. Okay, this is just application of definition of the star convergence and uniform boundedness principle. Okay, so second option. Hmm. If Fn is from L infinity star given by Fn of x equal to xn. Okay, so nth component. Then Fn has a weak star convergent subsequence. Okay, point two. Let Fn has a weak star convergent subsequence. Subsequence say Fnk, right? And say that Fnk converges to some f. So we have seen that this like star convergence. We have seen this happens if and only if Fnk of x converges to fx for all x belongs to L infinity, right? But what is Fnk at x? It is just x and k, right? This converges somewhere, like something is there. I don't know what it is, but what we know is this: for every sequence in L infinity, if you consider this subsequence, this index subsequence x and k, then that is convergent. But this is absurd, right? Like this statement is saying that for every sequence in the sequence bounded sequence, this nk subsequence will always be convergent. But this is totally wrong. You just define a sequence like on these positions you put alternate 1 minus 1, so this will be not convergent, and on other position you can put 0. That sequence still is in L infinity, but x and k is not convergent. This is absurd. This is not true. Now, third option. Every bounded sequence in L infinity has a weak star convergent subsequence. Okay. So L infinity is here thought of as L1 dual, and L1 is separable. Yeah. Okay, just L infinity is L1 dual. This implies unit ball of like L1 dual is metrizable, and by Banach-Alaoglu, it is compact also. So compact metrizable implies sequentially compact. So every bounded sequence must have a convergent subsequence. Yeah. Okay. Sequentially compact means this actually. Every bounded sequence will have a convergent subsequence. Metrizable means that Weak-Star topology can be metrized. Okay, in the unit ball. Okay? That is the result. Actually, it's a higher result. But, okay. That's how this option number third is done. So now question number 9. Okay. Which of the following statements are true? There exists an infinite dimensional closed subspace of L1 which is reflexive. Okay. Let W be an infinite dimensional closed subspace of uh, L1. Suppose W is reflexive. Okay. And since L1 is separable, Eberlin-Murlian theorem, what we have is every bounded sequence will have uh, every bounded sequence will have a weakly convergent subsequence, right? So if you take Xn such that Xn belongs to W, the subset, so that norm of Xn is less equal 1, right? Then Xn has a weakly convergent subsequence, say Xnk converges to suppose X, which implies Xnk converges to X, like this is weak convergence in L1 also, correct? So, but by Schur's lemma, weak convergence is same as non-convergence in L1. Right? That means Xnk converges to X in norm, like in L1, right? So that means also Xnk converges to X in W also, like because W is just a subspace of L1, right? So what we have is basically you have started with a sequence in the unit ball of W, then we got the sequence as a subsequence which converges to X, right? That means W is sorry. That means the unit ball of W is compact. Why? Because you take any sequence in that, it has a convergent subsequence, right? So, but that will imply that W is finite dimensional. This is not true. We have started with an infinite dimensional space W. So any infinite dimensional closed subspace of L1 it cannot be reflexive. Okay. So ninth is done. 10th, sorry, ninth B option. What it says is let V be a reflexive Banach space and T, okay, is set of all linear functionals from V to L1. If Xn is a bounded sequence in V, then sequence Txn has a convergent sequence in L1. Okay. B. Xn is bounded in V, implies Xn has weakly convergent subsequence with its reflection in Banach. Say Xnk. Okay. Now which implies Txnk is weakly convergent in L1, but by Schur's lemma, again Txnk is like norm convergent. Yeah, that's what we wanted. Then sequence Txn has a convergent subsequence in L1. Yeah, that's true. So now third option, V be a reflexive Banach space, same T is from L to V. There does not exist an S from L1 to V, so that T composite S is the identity map on L1. Okay. C option. I'll write here only. Okay, let's start with some Xn sequence. Be a bounded sequence in L1. Uh, which implies S of Xn is bounded in V. And V reflexive Banach implies Sxn as weakly convergent subsequence, which implies Sxnk converges weakly. Yeah, sure, I'll send the video. That means T composite Sxnk converges weakly in L1, right? But what is T composite S Xnk? Supposed to be identity, right? That means Xnk converges in L1. Yeah, because by Schur's lemma again, weak convergence implies norm convergence. So what we got is we started with a bounded sequence and we got a convergent subsequence also, right? That means every bounded sequence has a convergent subsequence. That is not possible because L1 is not compact. Okay, so this is wrong. Option 9. Okay, so we're done with 9th. So 10th, I have some problem in that. So I'll just send the solution of 10th one in the uh, assignment. Sorry, the solution sheet. So other than that, if you have any doubt, you can ask. Okay, do you have any doubt?